What is the electric field, by the way?
Oh, an electric field is the presence of electric charge.
Okay, it's not necessarily, because it could be generated by other methods.
A magnetic field as well.
Exactly.
Because they're complementary.
So so first of all, what is a field?
Oh,
Come closer. I don't see in your screen.
a field. Well, a field can be described by a vector, but then it's a vector field.
As a vector field. So
yeah.
Generally speaking, a field is a space.
Yes.
Where in any point
there's a
you have a different value. In this case, if we have an electric field, it's a vectorial field. So you have in any point of the space a different vector pointing somewhere else, in some not random in this case, but in some position, some direction. Sorry.
Yes.
And with a different magnitude. Okay. How do you say that here there is an electric field?
There's either a source or a sink of an electric charge. So you can either have a positive charge,
okay,
which radiates,
electric field,
or a sink.
Okay. Okay, and what happens when you have a charge which generates an electric field? How do you see the effect?
Oh, there's an electric field that emanates.
Let's say that you have a positive charge there, and then you have a negative charge here, okay?
Oh, they'll be attracted.
Attracted, so it means that there will be a force, right? If it's attracted, it means there's a force.
Yes.
Which tries to move, okay?
Yes, yes,
okay.
Yes.
Now, there is a force. You can measure it, okay? You go there with your charge, and you measure the force. The bigger, let's say that we double this charge here, the force will become
stronger.
Stronger, okay. It's reasonable.
But not double, because there's a squared, I think, in the...
Squared of what?
The radius is squared, I think.
Yeah, but the position is the same. We are at the same distance.
Yes, okay, yes.
So you double the charge, the force gets double. Okay. You make it 3 times triple, it becomes 3 times bigger, okay? So, the electric field, how does it relate to this force?
Well, I was going to say about the force between two positive, two charged.
You go there with your charge.
Okay, yeah.
You measure the force, and then you say, okay, I double the charge, the force gets double.
Yes.
Okay. So it's proportional.
It is.
So if you divide it by the charge that you put here to test the force, you get something which is independent on the charge.
Yep.
Correct?
Yep.
Because you put here 10 units of charge, the force gets 10 times bigger. So the electric field is something which tells you how large the force is there independently on the charge, because it's something that does not depend on the charge. If you increase the charge, also the force gets bigger. Okay?
Sorry, I just want to see it like this.
Okay, so the force, okay, fine.
Yeah.
So you can say that the force is the electric field times the charge, okay?
Yeah, yeah.
So it's the same thing, okay? Fine. Okay. So how large is this force? Do you remember? So let's say that you have here, let's call it Q1, Q2. So you will have a force which attracts the two opposite. Okay, so You call it R, okay? Fine. So how large is this force?
Okay, so there's a constant, which I think is 4 pi, and then I think the electric
Epsilon
permittivity,
0.
and then it's Q1 multiplied by Q2 over the radius squared.
Okay. Just to be precise, but in this lecture we want to be too much precise. We want to understand
Just the base,
the
concept.
meaning, the concept.
Yes, yes.
So the charges have some sign, the positive, negative sign. So,
Yes.
so we take the absolute value because, okay, we want to understand. This is actually the magnitude of the force.
Yeah, there's no vector component here.
And this is epsilon 0. Fine. Okay. So let's keep this equation here. Okay. So this is the force that you feel.
Yeah, the electric force.
The force given by these charges which attract each other. Let's say that we have this positive charge, okay? Let's call it Q. So we have an electric field which radiates. So
Yes.
try to draw it.
Oh, okay.
Okay, so in 3 dimensions. So yeah, unfortunately we have only the board, but now
Okay, yeah, but
let's say that we have a sphere. Okay, so this is the center, and let's say that we have a sphere. Let's say something like this. Okay, I'm not very good in drawing, so and we want to calculate the flux of the electric field on the surface. First of all, what do we mean by flux? Flux over a surface. Not necessarily, this is a closed surface. But generally speaking, if you have a surface...
Yes. Okay, so flux will be the amount of vector fields that are exiting the surface or entering that surface.
Okay, so let's say that we have this, there's not a surface, but let's say that we have this ring, and the surface is defined by the surface here of the ring. So if the vector enters, it contributes to the flux, because there is something going inside. If the vector goes
orthogonal,
so it's
parallel to the surface.
Parallel to the surface, so not...
it does not contribute to that
It doesn't
flux.
contribute, so it must be through the surface. Okay. If it's skewed...
it still contributes.
But?
But only the parallel component to it contributes.
Or the orthogonal.
Yeah, so if we have this surface we are talking about, and we have a vector field coming out, it must be orthogonal to the surface.
So let's say that, let's define our surface. Sometimes I realize that it's better to draw on the board surfaces which are not circular, because you don't see orthogonality.
Yeah, exactly. Like this, like it's two circles.
You don't see. But here I had to draw a sphere, because then you will see why. If you draw something like that, you see that it's somehow like perspective and so on. So let's define the S as a vector which is orthogonal to the surface. And the length is 1. Okay, so it's unit vector.
Okay.
And if you have a field which is not parallel to the S, so orthogonal to the surface, but it's cutting the surface, let's say this way.
Then, the contribution to that field is 0, because it's orthogonal.
No, it's skewed. It's not parallel. It's like this.
Okay. Okay, so then,
well, let's say that this is the electric field E.
Okay, so we have this ds, right?
Okay.
And
here's some angle.
Here's the surface.
Okay, so we are watching now in this direction, right?
Yeah, and now there's an angle.
Let's say that the electric field is like this.
Okay, so we need to see how much of this vector contributes in this direction.
Okay, so what you do is to take
The dot product.
The dot product, okay? So
And
you take the component of E
dot ds.
dot ds, which is,
What do you mean, which is? Do you want the, like...
yeah. So it's the cosine, so it's E.
Oh, it's the
Yeah.
it's the magnitude of E, dot the magnitude of ds.
Which is 1.
Okay, dot cosine alpha.
Okay. So you have E cos alpha, okay?
Yeah, because ds is a unit vector, which is 1.
Cool. Now this is E cos alpha, fine. Now we know what, well, this is for one point. If you want the flux,
You would need a vector field.
no, you need,
A cross product.
flux means that you want all the contribution of the electric field through the surface.
You need to integrate it over that surface.
Exactly. So you have to integrate over the surface. So you do it for all the single points of this surface.
Yes.
So if you integrate
E with respect to ds.
ds over the surface,
So it's a surface
okay,
integral.
you get, that's called flux, electric flux. I don't know if there is a specific name, but if there is a specific symbol, it's just flux, electric flux.
Yeah,
okay?
exactly. Yeah.
Fine. Okay, now we know what is the electric flux. We have to take a surface. Generally speaking, the flux is defined on any surface. We watch at any point the vector orthogonal
To that
to that
surface.
surface, ds,
Yes.
and we watch the component of the electric field in that direction, and then we integrate all over the surface. Now, let's go back to our sphere, okay? Here I have Q, and I know that it generates this force,
Yes.
okay? Now, I want to know which is the electric field at the radius r here on the edge of this ball. Okay, I have a ball which has a radius r. It's
Positively charged.
inside there is a charge, and the electric field here on the edge of this ball, or here, in fact everywhere, because on any point of this ball you are the same distance from r.
Considering there's nothing around that.
Yeah, let's say that the Q is in the middle of the ball. So on any point on the surface of this ball, you are always at the same distance, okay?
Yes.
So the electric field is, we said, this force.
Multiplied by the charge.
Let's say that you put a charge here, okay, divided by the charge.
Yes.
So try to plug it in. Let's say that here you put Q2, and this is Q1. So inside the ball there is Q1. Here you put Q2, you feel a force, and what you get? The electric field is, just take the force and divide it by Q2.
Okay.
Just try to write it down.
Well, this one cancels out.
Yeah, just write it here.
Yeah. Sorry.
Leave the equation there. So 4 pi epsilon 0 Q1 divided r squared. Cool. Well, in this case we used
Sorry.
small
I just wrote
case
it.
r. No problem.
Okay.
Okay. So here on the surface we know that the electric field is Q1 divided r squared 4 pi epsilon 0. Okay.
Yeah, by some constants.
Now let's try to calculate the integral of that all over the ball, all over the surface of the ball, okay? So you have to calculate the integral over let's call it S.
Yeah, so S.
This is a closed surface.
Yes. So that means there can't be any holes.
S. Of what?
There can't be any holes in the surface.
Yeah, sure. So it's totally closed. So
yes.
the flux we say is
ds.
Okay. In this case, in fact, the field is always radial. So you don't need to make any dot product because you are on on a surface. The charge is in the center. So it's always radial. So in any point of the surface is pointing radial. So you just have to take the integral of this all over the surface, okay? So try to write down this expression, so
just copy and paste?
Yeah. 4 pi. So this is the integral over the closed surface S.
Oh, because, oh my God, yeah, because it's describing the electric field. Okay, yeah.
So this is the electric field.
Yeah. Yeah, exactly.
And you integrate it over the surface. This is constant because we are on each point of the surface is constant.
And this is still a vector, right?
Well, in this case, you don't. It's just a unit of area, a infinitesimally small unit of area.
Okay, but it's still, but it's not, isn't it? It's the orthogonal vector coming out of this.
Yes. Okay, but it's referred to this point. If you integrate all over the surface, you get the surface. Okay? So if you get this constant out of the integral, what you get?
Well, so you just pull this out, so it's 1 over 4 pi epsilon.
4 pi epsilon 0.
Q is
Q1
constant, yeah.
R squared. Then you are left with the integral of ds over the surface.
And then we just get the surface equation for a sphere.
Exactly. Let's continue from here.
Okay.
1, 4 pi epsilon 0, Q1 over the radius squared.
And now the surface area of a
surface of the area is 4 pi r squared, okay?
Okay.
So.
Oh, then the r squared cancel out? Oh my God, okay, I see it. Wow. Epsilon naught. Insane.
Okay. That's, I don't know how they call it.
That's the right-hand side of the first Maxwell's equation.
Yes,
Gauss's
that's Gauss equation, something like that.
Wow.
So that's why, so this is the derivation. Okay, so we started from the force, which is something that you can test. So you put the charge, you feel the force, then you describe the electric field, and then you just apply the mathematics, and you find out that if you integrate the flux of the electric field on a closed surface, you find out that it's equal to the Q, to the charge inside, divide epsilon 0, okay?
Okay, and now this 4 pi, because this also comes from that there, but this is because the charge is a sphere, not because...
No. Well, the charge is not shaped. The charge is there, it's a point.
But it's not a spherical point?
No. The spherical point doesn't make sense. It's a point, it's there.
Oh, yeah, okay.
Well, in fact, if you have an object that has a random shape and is charged on its surface with different charge, as long as you know the total charge on the object and your surface surrounds that, it doesn't matter. This force that we defined before, it's defined for, it's given for a point charge. If I have an object, for instance, a plane, okay? Well, not very good plane, but...
Oh, I see it.
So where you have different charges, okay? Uniformly distributed. So there is a uniform distribution of charge on this plate. And you're here. Which force do you feel? Let's say these are all negative, and this is positive. Well, you can imagine that each of these points
would contribute towards it.
To one force in this direction. So
yes,
this will be this will create a force in this direction. So the force will be the vectorial sum of all the individual all individual forces generated by the individual charges. Okay, but that's not so important. Okay, now let's keep it simple. Let's say that the charge is a single point. Okay.
Okay, so we're going to write the first of Maxwell's equations.
Okay, so first Maxwell equation. Try to summarize what we have seen so far.
Okay, so it's called...
I don't know if they can see. Yes.
Okay, it's called Gauss's law. I know, it's the name, but of electric fields.
Okay.
Okay, and it states that the surface area, we'll call A, of the electric field vector with respect to a point on the surface is equal to the charge inside that surface divided by the electric permittivity.
Okay. Here use the S, so let's call it S just to be...
Oh yeah, pardon me.
There. Okay.
Yes.
So that is what we have seen. Okay, we in fact observed the electric field and we calculated, in fact, the integral over a surface, and we realized that it's equal to Q divided by epsilon 0. Now,
sorry, just a tangent here. When I was studying this equation, we were using a surface area, not a surface.
What do you mean by surface area?
Well, okay, so in the pictures that I was in the video that I was watching, it was always using a plane. But in this case, it's a sphere, right?
Oh, no, wait. This applies only if you have a closed surface.
Okay, yes. But it doesn't mean... So it could be like a piece of paper or it could be a sphere.
No, a piece of paper cannot be because it's not closed. If you take... Look. Let's say that...
Oh, okay, so... Okay.
This is a piece of paper, okay? Itself is not a closed surface. So, this is a very interesting point. I didn't want to get here now, but since we are talking about this topic. Now, for simplicity, I said, okay, you have your charge here, let's say it's a positive charge, and I take a ball where the charge is in the middle, okay?
Yes.
And then we calculated it. But what happens if the charge is not in the middle? This is not really a good middle.
Okay, so it's offset somewhere.
Instead of being here, the charge is here, okay? And then you calculate again. So this is a sphere.
So now at each point, the flux will not be equal.
Exactly. So here, no, the flux is defined on the electric field will not be equal. The flux is the total, is the integral. The flux.
But wouldn't the flux in this area be less than the flux in that area because it's closer to the source?
Flux is the total. Flux is the integral over the whole surface of E ds. Okay.
Okay.
The whole surface. So here, E will be, let's say, E1 will be bigger than here, okay?
Yes, most definitely.
Because here you have, I don't know.
Yeah, it's closer to the source.
Let's say this is R, and this is R divided by 2. And here the radius is R plus R divided by 2, okay? So definitely here it's closer to the source, so it's bigger. Here is smaller, okay? So when I start integrating, I find out that here there's more contribution to the flux and here less contribution to the flux, okay? But the total flux doesn't change. When you make the integral over the whole surface, okay? So you take the whole surface of the ball, the total flux doesn't change. This is the beauty of this law, that you can put your charge wherever you want, okay? And locally, you have more or less contribution. But in total, the total flux never changes as long as the charge is inside. Okay?
Okay.
So because here there is more and here there is less. So in total, now I'm not very formal in this explanation, but intuitively you see that here there is higher concentration of flux, here there is lower concentration of flux, but the total flux will be the same.
Okay.
So you can put your charge here, 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 even here, very close to the border. Doesn't change, okay? But this trick works only if the surface is closed.
And if the surface is uniform?
No, even if it's not uniform. Let's say that you have a cube, or maybe even not a cube, but something shaped like
with
this.
straight lines.
Okay? So maybe it's closer to the top. Let's say this is still under, okay? Okay, still under it's inside this,
yes.
This structure, which is definitely not, how did you define it? Uniform?
Yeah.
It's not a sphere, but doesn't matter. Still, here on the top you will have bigger electric field because you are closer to the charge. Here you will have it smaller, but it doesn't matter. Once you make the integral all over the surface, all the faces of this figure, still you get the same flux. This trick, however, applies only. Are you confused?
No, just thinking. Please carry
what?
on. No, it will take you off from where you were going. So I'll ask it afterwards.
Okay. So this, however, applies only if the surface is closed.
Okay.
Because if the surface is closed, then you can, in fact, say, okay, here is bigger, here is smaller, but somewhere the flux has to go out. Okay, so you can have bigger or smaller flux, but in total, the charge is there. The charge generates some flux, and either it goes out of here or goes out of there. Somewhere it has to go out.
Yeah. So
there's no route where another route where it can go exit.
Yeah. So the flux density is different in certain areas, but when you sum the density together,
Exactly. The total flux is the same. Okay. This is your surface. It's attached to this ring, but it's not closed. Here there is some opening. Okay. So let's say that you have your charge here. Some flux will get out of here, and some flux will go through this surface. If I have my charge here, clearly the flux which gets out of here is smaller because I'm far from the charge.
Yes.
And the flux which goes out of the back is bigger because my charge is there, close to the back. So you see that if you compute the flux over the back, it changes according to the position of the charge. If my charge is here, still there will be some flux line which arrive here, but just a little bit because it's far away. So this trick doesn't work anymore. If you have your charge inside the surface, okay, let's say that inside this volume, here a part of the flux will get out of here, and it will not contribute to the flux of the surface because it is escaping from this opening. And how much is it escaping? Well, it depends where is the charge. If the charge is here, close to the edge of the back, a little portion will get out. If it's here, close to the opening, a large portion will get out. So of the total flux, the part which escapes and which is not computed depends on the position of the charge. It's not constant.
Okay, but now the fact that this is not a closed surface will change the way we solve the magnetic flux exiting the surface area.
Well, no. The flux itself is computed in the same way. You still have your vector, which is
orthogonal, to the
orthogonal,
surface.
and you compute for each point the field or the dot product of the unit vector times the field. Okay.
But it would not be as easy as this equation.
Of course, it's not really, but I don't want to enter into.
Yeah, of course. Just.
I don't want to enter into how you solve it. Just intuitively, now you.
Oh yeah, of course. So yeah, it's basically the density will be different if it's here and if it's there.
Okay. So if you have an opening, there is some way where the flux can escape. Out of the total flux created by the
charge.
By the charge, some part can escape, and this part which escapes is not computed as
On
the
the
flux
surface.
on the surface of the flux. The point is that the part which escapes depends on the position of the charge. So if you have the charge here, you have more charge escape, and therefore the remaining flux which goes through the bag is less.
Yeah.
So it's not constant. You can say that the flux is, let's see if I have another bag. So if you can say that you have always the same flux if the bag is closed, okay? So here you have the bag is closed. If you have a charge inside, I don't have it, but let's pretend there is a charge inside. Now, all the flux is computed because it's surrounded completely the charge. So somewhere the flux is going out and you always intercept it. It cannot escape, okay?
It cannot escape the equation.
Yeah, it cannot escape the surface, so it's always computed inside the flux.
Yes.
Okay, so this equation applies only if there is
a closed surface.
A closed surface, okay? What happens if there are two charges inside?
Okay, just before we carry on.
What do you want to do?
Okay, so we had a cube, or some rectangular version of it. And if we're just going to solve this equation, or pardon me, that equation there where it's just the surface area of this cube, we would just basically take length times breadth and then times it by 6. We would need to get the surface area of this cube in order to calculate the flux leaving this this cube. So we would just get the surface area, which would be length times breadth, and then times it by 6.
No. It's not so easy. Wait, if I can. Let's say that here there is a charge.
Yeah.
And we are watching from the top view, okay? From the front view. So you are watching here the cube. Here there is a charge, okay? And it's a point. So this is the charge. You have to take here the field and at this direction and this at this point, and the field here it has, I don't know, distance t. Then for this point, for instance, what you have to do, you have to calculate d prime, which is this direction, okay? So here the field will be E prime, which has another value, because here it will be given by the force at this distance. Here the distance is larger and the force will be lower, because remember that the force is 1 divided by pi, 4 pi epsilon 0, the charge, divided by the square of the distance. So you are more distant, so the force will be lower, therefore the electric field will be lower. And then you have to calculate ds, however, is, you see, it's always in this direction. In this case, it's parallel to E. Okay? In this case, it's not parallel to E. So what you have to do is to calculate this E prime times cos alpha, okay? And the same for here. So you get a point here. You have, this is E double prime. And again, you have to calculate only the component which goes per orthogonal to the surface. So again, let's say this is beta. And So this will be the component E double prime at a distance d double prime times
Cosine
cosine
beta.
beta, okay? And you have to do it for all the single points, okay? This gives the flux through the surface. Actually, you have to do it in 3D.
Yeah. So making it like a square object or square surface area would be a lot more difficult than a cylindrical or spherical.
If it's a sphere, it's
yeah.
All the distance is always the same. So
well, it's easier because it's in polar coordinates, right? Because you can just have your angle and your radius that moves around. Well, this would be easier because you could just use polar coordinates when you're solving it, because you just have your angle and your radius that moves around the circle.
If you want, let's make it as an exercise.
Oh. Because this would be Cartesian, right?
And I've never did it. So yes, you can maybe in cylindrical bow. I don't know, but also I don't know.
Okay, but yeah,
let's not complicate our life.
Yeah. This was already just an example of how difficult it can be if it's
So anyhow, you have always to check the component of the electric field which leaves this surface orthogonally.
Yes.
So at each point, you have to calculate the component of the vector which is orthogonal to the surface. So it's uselessly complicated. Okay. But yeah, generally speaking, if you have a cube and it's closed because it's a cube, if you make this calculation, you should get again to the total flux, which is Q divided by epsilon 0. Okay. Let's say that I still have my ball, and instead of one charge,
you have
two charges, but with negative sign, with opposite sign. How does the electric field look like?
Oh, okay.
Nice shape. Continue. Don't be scared. And the line which goes out of here, where does it go? Continue. This one? Where does it go? Hey.
Oh, I see.
Oh, okay, fine. So.
And then this, yeah.
Okay, fine. So what happens when you calculate again the electric flux?
It's no longer the amount of charge that's in the ball.
In fact, it is.
It is?
How much is the electric charge in the ball?
Q1 minus Q2.
Which is? If the two charges are the same.
Oh, zero.
Zero, okay, so.
But then, but there's still flux coming out.
Hey, then wait. Yes, it gets out.
Oh, but probably they will subtract, because this is entering, that's exiting.
Exactly.
And then the net is zero.
Of course it's going out, but if it's going out, it returns back inside.
It's a dipole, so it's zero.
So in total, the flux
is zero. The flux exiting the surface area is zero.
It's zero. Some is going out, but some is returning back. If it goes out, it returns back. So total is zero. And this is okay, because our law tells us,
I'm listening,
that this is the total flux of the electric field through our surface, okay? This is our surface S. And we saw that if we compute all the flux around the surface, it's zero, because if there is one line which goes out, eventually, sooner or later, it will return back, okay? So this is zero. But how much is the charge inside this ball, the total charge?
Q1 minus Q2, where Q1 and Q2 are equal, so it's zero.
It's zero, okay.
Yeah.
And this apply again, I draw, for simplicity, the two charges symmetrical.
What about these ones? How do those go back there?
Sooner or later, it will return back. It could be like...
Yep.
It always returns back, no matter what. It could take far away, but it will always return back. What I was saying? Yes. Again, in this situation, I have drawn the situation quite symmetrical. But the same applies if, for instance, I have, let's draw a very extreme case. Let's say that I have still my ball, and I have a charge here, and a charge here. Okay. Again, I have the same configuration. Of course, here I will have more flux incoming. So the flux density here will be very large. Here, the density of the flux will be lower because it is spread over a bigger surface. But again, if you take the integral over the whole surface, the sum is 0.
Yeah.
Okay. This is the beauty of this equation. It doesn't matter where you put the charge. So a better description of this equation. So let me write it here. Is by writing the charge as an integral itself. Okay? So instead of writing the equation like that, we will say again that this is the flux over a closed surface S, okay, of E ds. So this is the flux over the closed surface, is equal to the total charge divided by epsilon 0. But what is the total charge?
Oh yeah. The charge can also be described as the charge density.
So let's say this is the charge density.
Yes. Over dV.
Over dV. So we take the whole volume inside the ball.
Yeah.
And we watch the charge density
within the ball.
So if we take the integral of all the charge density inside the ball,
that will be the charge.
That will be the charge, the total charge. Okay?
But this you can also just express as a rho is equal to Q over A, and then the A becomes the integral. Pardon me, not A, V. And then the V becomes the integral.
It depends how it's spread. Let's say if you have a uniform
surface
volume with uniform charge, okay, but for instance, if you have a ball and you have one charge here, one charge here, one charge here, let's say this is Q plus and minus Q, okay? So when you start integrating, you have 3 coordinates, X, Y, Z, okay? And you start integrating this point, 0, 0, 0, 0, 0, 0, 0, Q, 0, 0, 0, 0, 0, 0, Q, 2 Qs, 0, 0, 0, 0, 0, 0, minus Q, 1 Q. That's it. So when you integrate all the points inside the volume, of the volume inside the sphere, the density is 0 everywhere, unless these 3 single points, which give you the charge, okay?
Yeah.
Okay.
Yeah.
Fine.
Oh, but I was just saying here how you can say that this is valid, is that the Q, because then Q is equal to rho times V, and then the V becomes the integral. And then,
okay,
but so that's just basically how you get that.
If rho is uniform all over the surface, you mean? All over the volume? You can multiply times the volume?
Oh, yes. But because it might not be, you have to integrate it, so you add each component individually. Yeah.
Like, if you have let's say that you have a ball which magically is charged, it has charges uniformly distributed in the volume, you have the density of charge per unit of volume, then you multiply times the volume, and you get the total charge. But generally, you have points with individual charges.
Yeah, with no charge or with charge. So the integral will find those points.
Now, Why did I write this equation like that? Not just because I like to write.
Oh, because we're getting away to the differential form of
Exactly.
Maxwell's equations.
Exactly. This is integral form, which describe.
Integral form is for like, let's say, nice areas that we are trying to
Define nice.
spheres, cylinders.
No, any sphere, any shape. The integral form.
Well, for the wouldn't the well, okay, I'm not actually familiar with how the differential forms work, but wouldn't, like, if you're solving the Maxwell's equation in the cube, wouldn't it be better to do a differential form and then just have a computer iterate through it?
Wait, probably there's a misconception about that. So let's say that you have a nice, very regular shape, and namely, we will use a ball. Okay, again. I have here my charge, positive charge, so I will have an electric field like this. Okay? And I have a ball. For this ball, the surface is S. We have this equation, so the integral of E over the surface is the total charge inside.
Yes,
okay?
yes.
As you see, what we are doing is using integrals. It means that we consider the total flux around and the total charge inside. But let's try to go smaller. Instead of this ball, we use a smaller ball. Okay? Still the same.
Yeah.
Okay? And then we use a smaller ball, still the same. And then we use a smaller ball, still the same. But let's go even smaller ball, still the same. Now, go to the point. Go to the situation where you don't have any more an area. You just go
to the point.
So small, infinitesimally small.
Okay, well, I'm thinking of a limit now because.
Okay, so let's make the limit of this ball shrinking
to infinity.
Small. Now,
to zero.
You don't have a total charge anymore because you don't have a volume. Here you define the density of charge per unit of volume, okay? But now you don't have a volume anymore.
Yeah.
So what you have, just in a single point, you just have the density of charge.
So we need a function that describes the density at points.
You have it. It's raw.
Okay.
This is the density. If you are in that point, you don't have to integrate over a volume because you don't have a volume anymore.
So wouldn't this make rho a vector? Because if,
no. The charge is a scalar. The charge is how much charge you have in that specific point.
Yeah, but
wait a point. So, in that point, you don't have a volume anymore. So, you just have, so you cannot make the integral of the charge over volume, but if you are in a point, you just get the density of charge in that point. It's not more complicated, less intuitive. What happens for E? When you described this ball, you were watching how much the field was leaving, okay? Okay, that was how you described the flux going out from the surface. What happens when you go to the point? So, if you don't have a surface anymore, but you are just here in this point, you have to watch how the field explodes, okay? So, you don't have the integral of the field leaving a surface because you don't have a surface anymore.
Yeah.
You get here, and in that point where you have the charge, you have all the lines of the field which are exploding, okay? Why they are exploding? Because there is a charge. If, for instance, you shrink your ball, okay? Let's say that again you have your ball, with the charge here. And you shrink your ball, but you shrink it here. Now the field does not explode. It passes by. Okay? Now you can describe different fields according to the shape the field F, the field S. Okay? So, for instance, if you have a uniform field, let's say that, for instance, you are in a capacitor, ideal capacitor, you have a uniform field, okay, charge is positive, negative, okay. So here, you don't have any explosion, okay, because if you take your ball and you shrink it, shrink it, shrink it, here the field passes through. It gets from one direction and leaves from the other one, fine. Here is different. Here, the lines have a different shape. If you go to a single point, and that point is the point when you have the charge, you have this explosion of lines, boom, getting out of from any direction, okay? So,
but this still means we're thinking about a ball, because if it's going,
no,
and here we're thinking about a surface area.
no, it's still a ball. Let's say that you have a ball.
Well, no, wait, because if you take a square and then you can see that, okay, the flux lines are passing in one direction.
Okay.
But here, if you were to, okay, let's say if you were to take a square, they would still be passing, well, they wouldn't be passing out in one direction, they'll be passing out in every direction.
Well, I don't take a square, but I take a closed surface.
Okay.
So at most it's a cube.
Okay, a cube.
And still I have the same problem. Let's shrink it down and go to the single point.
So we're at the charge.
We are at the charge. There, we need something which tells us how the field explodes.
Yeah, the curl.
No?
Okay, the
The
divergence.
other one.
The divergence.
Divergence, okay. So, the divergence is basically, is telling you if in that point,
There's lines leaving or entering.
Exploding. Because if you are here and you have a uniform field, let's say in all direction, the flux is entering and then leaving.
Okay.
So there is not an explosion. Let's think like...
Okay, but what would the divergence of this field be? Would it be...
Zero.
Would it be zero?
Because there is not net explosion. Let's think in like... let's think into divergence. If you have negative divergence. Negative divergence, what does it mean?
The flux lines are going in.
Okay, so if here in this point I have negative divergence, it means that all the field goes down there, which means that there is a sink which
negative charge.
Sucks out all the field, and they, boom, disappear. Like it's a black hole which, oh my God, this is technically so wrong, but okay, just imagine that there is something magically which take inside. And it doesn't go anywhere else, so it's just sucking everything inside. This is not true if you have a uniform field. If you have a uniform field, there's nothing disappearing. Okay? If you are here,
just passing
something arrives, but something leaves.
Yes, yes.
Nothing disappears.
Okay, I got you.
So there must be something that gets everything inside and doesn't let it go anywhere else. This is not the case because it enters, but then leaves, so nothing is lost. When you have a negative divergence...
Yeah, the flux lines are all moving towards that point.
Exactly. So if you have negative divergence, everything goes inside, and boom, magic, there's nothing anymore.
Okay.
So, and of course, if you have positive divergence...
Yeah, they're leaving that point.
From this, if you have positive divergence, they all leave out of nowhere. Boom, explosion, like a bomb, that you have a bomb and it explodes in all direction, okay? So that's why the divergence tells you that there is an explosion, if it's positive, or an implosion, I don't know.
Implosions going in, explosions going
Yeah.
out. But now, okay, so 2 questions. I was trying to think maybe this is related to a limit somehow in vector fields because we at a single point. But that might be stupid. And then the second point is if the divergence of the electric field is greater than 0, that means the charge density is greater than 0.
Yes.
And if it's less than 0, the charge density is negative.
Yes.
And if the divergence is 0, that means there's either
Zero charge.
no charge or there's an equal amount of positive and negative charge.
Well, we are in a point, so
Okay, so then there's no charge.
zero charge. Yeah.
Okay, yeah, okay.
That's exactly like that. So,
But what about the limit thing that I said?
no, the limit is simply what you are doing here. So you go from a situation which is global. This is probably the objective. Global and local. This equation describes a global situation. So something that describes not a point, but a volume, a surface, a finite, a non-zero, finite non-zero surface and volume. So something big, okay?
Yeah,
it's
yeah.
not so technical. Here, so you go from the surface to the point. Here you go from the volume to the point, okay? So these are the two. Of course, then if you integrate this over,
You get back to that.
you get back to over the surface and the volume, you get that. You integrate this charge density over the volume, you get the total charge. So, okay.
Okay, but also this, the del operator, is actually partial derivatives. It's
Okay, we won't enter to explain.
oh yeah, but that makes sense because then basically the derivatives.
The derivative tells you how much it's changing. Okay.
Yeah, at the point.
Exactly. So you're in a point, and how do you calculate the divergence? You sum the partial derivatives of the of E over the free components.
And that gives you the slope of the field.
The rate of change of the field. So here you are concentrating in a point, boom, it explodes. So it tells you, boom, it's getting bigger. There is a derivative.
Yeah, there's a positive derivative, it's
or
exploding.
negative.
Yeah.
So this is how intuitively you can understand. So this is the first equation. Okay.
So if we take the volume integral of the divergence of the electric field with respect to the volume, that should still equal that, right?
Mm-hmm.
Okay, but now let's not just state that, let's explain why. Because these are derivatives and this is the area of that derivative. So we just sum them together and it should be the same, right?
So if you integrate over the volume the divergence of each point, you get the total flux leaving.
Yeah,
Why?
because this is the flux.
Let's again, equations are fine, but let's try to think about the physics. So you have a ball.
Yes.
And you have the field, which has, I don't know, divergence, positive here, positive here, negative here, because you have a negative charge here, okay? Plus Q, plus Q, okay? So what you do is to integrate the derivative of all the volume. And all the points here have derivative 0, but these 3. Okay?
Yeah.
So when you integrate the derivative, you make these two, the derivative compensates each other.
Yeah.
So they cancel each other, and you're left with one point with the derivative. So when you take the whole integral over the volume of the divergence, you get again the total,
the net flux,
the left flux, which is leaving, because here some flux will get back, but some flux will leave, and it will leave some flux only if the integral of the divergence inside the ball will be positive.
Yes, okay? Yes. Okay, so this is equal to the flux of the electric field leaving the ball, but that's also equal to the charge within the ball divided by the permittivity, right?
Okay,
so it's like that.
Mm-hmm.
Then earlier we stated that we can express the charge as the charge density over the volume, not mu, excuse me, the volume. And then that's if it's homogeneous or if the charge density is uniform. But if it's not uniform, we need to use an integral, right, for this.
So that's what we were doing here.
Yeah, exactly. So we can express, so then we can say that...
May I ask you why you are so interested in this case?
It's just, I don't know, I can visualize it. But I don't know, it stood out to me when I was studying it. I don't know why. Okay, so then now we can describe Q as the volume integral of rho 1 over epsilon as the volume integral of rho with respect to the volume, right? Okay, so now we can...
No, wait. The Q is the integral of rho.
Oh, excuse me, yeah, it's going to come here. So now, now we can say that 1 over mu multiply, pardon me, epsilon, multiplied by the volume integral of the charge density with respect to the volume is now equal to the volume integral of the divergence of the electric field vector multiplied, pardon me, with respect to the volume.
The volume, yeah.
Yeah. Now, well, those integrals are equal, so we can just cancel them out. And then we have, then we have mu over epsilon.
Rho.
Goddamn. So, rho over epsilon naught is equal to the divergence of the electric field. And then there's the differential form. That's how I saw it.
Yeah?
Because it's nice when you can just, cancel those things out.
Yeah. You like to erase. Okay. This is a mathematical approach. What I was trying to tell you is to understand that
the meaning of
the meaning.
Yeah.
Again,
and we clarified that with this because now we can actually know why that is equal to that.
So you understand. So you always try to think the meaning of divergence. Divergence means that there is a source.
Yeah.
If it's positive or a sink, which sucks all the field inside.
Yeah, where the vector field's coming from. Or is that vector field emanating or radiating?
Radiate. Nice. I like the verb radiate.
Yeah.
If you have radiating field, it's because there in that point you have a charge which generates. So if there is no charge, there is nothing radiating, so the divergence is 0, but then the charge is 0. If there is negative charge, it's absorbing, it's sucking in all the field. So you have negative divergence because it's... And therefore you have negative charge, okay? So that's the meaning. So try always to remember this concept. So I say, okay, I try to take a sphere and I have a charge inside. So I take the electric field and I calculate how large is the flux leaving the surface. So I take the integral over the surface S, a closed surface of
the electric field,
E ds, and this is how much flux is leaving. And then I say that it's the total charge which is inside the ball. So I say that divided by epsilon 0.
Yes.
So it's 1 over epsilon 0, the integral over the volume enclosed inside the surface of the charge density
over the volume with respect to the volume.
With respect to the volume.
Yes.
Okay. The only thing that you have to remember in this case is that that you have epsilon 0.
Yeah, but and that's just for the units, right?
Sorry?
Well, when I was studying this in the past few days, whenever they
we use SI here.
Whenever they use epsilon naught or mu naught for magnetic fields, they always say this is just to maintain the balance in the units.
It's a constant. If we're talking about the vacuum now, okay?
Yeah, yeah.
Okay, so this is a constant. So you could say, okay, I measure my charge density in another silly unit of measurement where it is E0 bigger. For the same charge, I have E0 bigger charge because I call it in another way. And then here, I don't need it anymore. Because by itself, I measure it in such a way that I call it a bit epsilon 0 times bigger. Okay?
Okay.
What is a voltage?
Voltage is charge difference between 2 points, or potential between 2 points. Huh? Voltage is EMF, electromotive force.
Yeah, thank you very much. That's just another way to call it. What is a voltage? Physically, what does it mean, voltage?
Voltage is the potential difference between 2
Yeah,
points.
potential difference. Yes, still same. Then you have to define what is potential. Okay, I have a charge here. This generates an electric field, okay?
Okay.
Now I have 2 points, point A and point B. What is the difference? What is the voltage between these 2 points?
Well, I would just say UA minus UB.
Yes, but what is U then? Physically, I have a charge here, okay? And I want to move it to here. I take the charge and move it here. What is the voltage? What is physically the voltage?
Oh, it's the force being experienced. The force that's...
It's not really force, but...
The electromotive force?
The force?
Being exerted?
There's a distance between these two
Yeah,
points.
yeah.
So it's the force times
distance.
Distance is the
Potential.
work.
Is the work.
Is the work
Okay.
that you have to make.
Oh my God, okay.
Is the work, the energy you have to make to move the charge from point B to point A divided by the charge itself. Okay?
Okay, so
let's say that...
Wait, hang on. So it's W is equal to D over Q?
Okay, here you have a charge.
Yeah.
Forget a moment for the equation. Here you have a charge.
Mm-hmm.
The charge is in this point. And let's say that it's a positive charge, okay? So it has the tendency to leave because here I have...
Yeah, there's a repelling
positive.
force.
So if you want to move it here, you have to...
Yeah, you have to put
Boom.
energy into
Okay.
it, right?
If you double this, the force will be doubled, and then...
The double amount of work will need to be put
Okay.
into the charge.
So if you take the work that you have to take to move the charge from B to A, divided by the charge that you put there, you get the voltage. Okay. Now, what is this work?
It's energy,
It's the force times
distance.
the distance.
Oh my God. Okay.
And this is the force, the electric force, okay? What is the electric field then? The electric field is the, in any given point, is the force divided by Q. Okay, so I put here, I have this force, and I get force. The electric field is the force divided by Q. Okay?
Okay. Force divided by Q.
Okay. So the electric field is the force divided by Q. Okay. What happens if you integrate the electric field on this distance? Okay. So you go from this point and you arrive to this point. So you take the integral of E from point A to point B, okay? Over this line, okay?
Well, it's going to sum up the electric field at each point.
Yes. So you sum up the electric field of each point, and what you will get. This is force divided by Q, okay? Okay? This is the Q that you put here that you want to move. So here you have A, B, times the L, okay?
Yes.
Let's say that this field is uniform, just to be simple.
Okay.
Now here it's not, so you should integrate something which drops down as the distance and so on. Let's say that this field is uniform. Let's say that we have a capacitor
Okay.
like this, okay? So you have positive charges here and negative charges here. Okay? And you want to go from point A to point B, okay? So you have your charge, and you have to move it over this distance, okay? In this case, the electric field is constant, okay? Yes. So the electric field is constant. So when you integrate, let's integrate this electric field over this length, okay? So the electric field is the force which is felt by this charge divided by the charge itself, okay? And you integrate it divided by A and B, okay? So the L, the electric field is constant, so the force is also constant. We can take it out, okay? Then you have also Q. It's also constant. It's your charge that you put there. You take it out. Then you have the integral of A from A to B of the L, correct? Which is what?
It's going to be FQ multiplied by L.
Is the distance.
Yeah.
Okay? So.
And then L will be B minus A.
So you have force divided by Q times the distance between the point A and the point B. So you apply a force to a charge, and you move the charge from point A to point B over a distance. What is force times displacement? If you apply a force to something and you move it,
work.
It's work. So this is the work that you have to make to move the charge from point B to point A, okay? And divided by Q. That is a voltage. So the voltage is the integral of the electric field between A and B. So if you have 2 points, point A and point B, and you want to know which is the voltage between those 2 points, you have to make the integral of the electric field over
the distance.
The integral of over the path from A to B. Okay?
Yes.
That's the voltage. So why did I say this? Because if this is a voltage, the unit here will be volt. Here you have the integral of E over the L. Okay? This is going to be meter. So what unit should be the electric field if when integrated over the distance you get volts?
Yeah. Oh my God. Yeah. Okay. Volts over meters.
Volt over meter. So if you integrate volt over meter,
they cancel, and then you have volts.
Over a distance, which is measured in meter, you get volts. That's why
voltmeters.
Volt per meter. Of course, then you can write volts in whatever, or a meter in whatever other units you defined, whatever. So if you want to say the electric field is force divided by charge, so force is Newton, charge is in Coulomb, fine. But, you know,
yes.
If you say Newton over Coulomb, doesn't tell you anything. if you say volts over meter, it tells you, okay, take this field here, you integrate it over the
distance.
some meters, over a distance. So if you integrate volts per meter over a distance, you get volts. Okay? So this is why the units of the electric field is in volts per meter. Okay? And let's consider again a capacitor.
Okay.
Ideal capacitor, you have all your positive charges here, negative charges here, and you have a uniform field, okay? The electric field inside is uniform. Then we have checked which is the work that we have to make to move from here to there, okay? Then let's try to make a closed path, okay?
Uh-huh.
So here you have to put some work to move. Let's say this is a
It'll be 0.
positive charge, okay?
Yeah, it will be V.
Let's say that you have a negative charge, okay? Negative charge will feel a force which tries to push it to the left because here you have positive charges, okay?
So you got to add work to it.
So you have to add work to move here.
Yes.
Okay, here we have to put some work to move from A to B, okay? So it's a positive work. You have to add some work to move here. Here, you move from B
0.
to C, 0, because we are always at the same distance from
The potential.
so it doesn't change,
Yes.
okay, no work. Here, we go in the opposite direction, so our charge is negative, and it goes in the direction that
It wants
it's
to go.
like.
So
okay?
it's negative work.
So here, the work is leaving when we go from C
To D.
to D, okay? So, and then, again,
0.
when it moves here, it doesn't make any work, okay? Because you integrate the field over there is no distance. We don't get far from the positive side, okay?
Yeah, yeah.
So, the total work is?
Pardon me?
The total work
It's 0.
0, okay. So if you take the total work, which is the work from A to B, then the work from CB plus the work from C to D plus the work from A
E to A.
D. Now, these two works,
Oh, 0.
BC,
0 and 0? No.
A,
DC is 0.
no,
No, wait, sorry. B,
No, no,
A.
no.
Yeah, you're right.
These two are 0, and this one are equal. So this is work that we inject,
Yeah.
and this is work which is leaving, okay?
Yeah. Which we get back.
Which means that you have the integral of E from, let's write it there, because otherwise we don't have
Yeah,
much
there's no space.
Okay, so we have the integral over A to B of E dl, okay?
Yeah.
Plus the integral
B to C.
B to C plus the integral
B, C to D.
C to D
And then D to A.
plus the integral. What was?
D to A.
D to A.
So we're getting to a line integral somewhere.
Okay, which is the total How do you define it? Like this?
And then L.
So of E over closed
Loop. And I think DL is also a vector. 0.
Because here we are going in this direction. It's 0. Okay. This is the base of Kirchhoff law.
Yeah.
So because Kirchhoff law says if you have a closed loop and you sum all the voltages, the total is 0. Because this is the voltage between the points A and B. This is the voltage between C and B. This is the voltage between the DC, and this is the voltage between AD. So if you sum all the voltages,
they're 0.
It's 0. And this doesn't depend on the shape. Okay? The shape could be...
It's just, it must be closed.
It must be closed.
Yeah.
Because whatever the path is, it will turn out that the work that you put there somewhere, you get it out somewhere else. If you go back to the work, to the starting point, okay?
Yep.
So it applies only if the line is closed, okay? So this is Kirchhoff law, which applies now in these conditions. There is a case where Kirchhoff law doesn't work, okay?
Where?
So what, are you scared?
No, just confused.
Confused? Fine. Yes, Kirchhoff law does, Kirchhoff. I asked my colleague who speaks German, he said Kirchhoff. Kirchhoff law of voltages works only in this case when you have an electric field which is conservative, which is not a political view, conservative because it conserves the energy, okay? You put energy to move a charge from here to here, and then you get back the same amount of energy. There is a case when this is not true anymore, and Kirchhoff law doesn't work. We will see it when we will see another equation.
Okay.
Maybe the Faraday one? I don't know how they call it.
Of Faraday's law of induction?
Probably.
Or Ampere's law?
Oh, yes. Faraday. When we are in Faraday law, this doesn't work anymore. Don't worry, we will get there.
We'll get there. Okay.
But you see that when you watch the physics, you understand why we have Kirchhoff law. You understand what is the voltage. Voltage is the integral of the electric field. Oh, this is, a very bad L. It appeared like a rho. Voltage is the integral of the electric field over a path. In this case, it's conservative, so it doesn't matter which path, whatever is the path. Like if instead of going straight, I go curved, still I have to put the same energy to go from here to here, no matter what. Okay?
Yes.
So again, it doesn't depend on the path. Okay? So the voltage is the integral of E over a distance. And we have seen why, because the voltage is the work you have to put to move a charge from one point to another divided by the charge. And we have derived that corresponds to the integral of the electric field over, over the 2 points. Okay. Fine. This looks fine. We will connect to this thing later. We will see why, in some cases, this is not true anymore.
Okay.
It has to do with the shape of the lines.
You mean of the
electric field?
Yeah.
So now the electric field has this shape. It applies. I was starting this example with the spherical, with the field generated by a point charge instead of an electric capacitor. But in fact, it applies also with the electric field generated by a charge. Let's say that you have a charge here, Q. It's positive, so it generates a field in this direction. And let's say that your loop will be like this. Okay, so this is the electric field. You have point A, B, C, and D. Okay, so let's say that you have a positive charge here, so that's why the field radiates.
Yeah.
And you have a test charge, which is negative. And you have to bring it from point A to point B. So it will feel a force attracting. So in this case, in order to bring it from here to here, I have to put work or remove it.
I have to put work.
So here, the work is entering, okay? So I have some work which enters. If I move from here to here,
you'll put a little bit of work.
ooh, it's at the same distance.
Oh, no, okay, it'll be zero. It'll be zero.
Okay, so
Okay.
here I move on a surface where I don't have to fight anything because I'm always at the same distance. So
Yeah.
if I move it here or here, I still have the same force.
Yeah,
So-
just because it's
so
radial.
Here, here, because here
Yeah, equal.
it's orthogonal. Okay, so I don't have to fight anything to bring it from here
Yes,
to here.
yes, yes, yes.
Then, if I move my charge from here, from point C to point D,
Well, it will be negative
negative going
towards Q.
towards Q,
Yeah,
so
yeah. So, negative work?
so it will release the same amount of work
Yes.
and back.
Yeah, to zero, because it's the same
zero, okay.
distance from the middle, from the origin.
So this is a special case which is simple because I used a closed loop which has two paths radial. So when you integrate E over dl, if this is dl, okay, so let's draw it here. Let's draw again
DL?
this.
Oh, okay, yeah.
So this is dl, and this is E, okay? Here is E, and dl is in the opposite direction, okay?
Test.
What?
Test. Okay, just, I sat on the thing. Don't worry, sorry.
So here, the integral is positive.
Yes.
So that's why you have work which goes inside.
Yeah, yeah, it's the surface area from the top line down to the bottom line.
Surface area? There's not an area, there's a line.
Okay, well, if we actually, well, here you would be using,
This is a line. You have integral, a line integral from point A to point B
oh, yeah.
of E
Yeah.
dot dl.
Just one thing, earlier when we had the square, square nodes, when you were doing integral from here to here, I was seeing this area.
No.
Wait. When you go down here to here, there's no area because it's a straight line. When you go here to here,
It's always a line.
It's this area, but it's negative. That's why the integral is zero. Because we weren't doing line integrals earlier. We were doing normal.
No. We were doing line integrals.
Oh, okay.
When we have okay.
Oh my God, yeah, it was. I even said it. Never mind.
So still, what we were doing is here you have an electric field which is in this direction, okay? Because here you have positive charge, here you have a negative charge. Then you draw this rectangle, and what do you have in this rectangle? The electric field on this section has the same direction of dl, okay? Here, let me draw it bigger. Okay, so let's say that we have this box with point A, B, C, and D, okay? Now, you have to calculate the integral of E of times dot dl over this distance to get the work that you have to put inside. Okay? So you have E as this direction. And for this segment, dl as this direction. Okay? So
Yeah.
E dl is positive. The opposite happens here because E is still the same.
Yeah,
You're
but
still, you have E in this direction, but
your distance is in the opposite direction.
the unit vector of the path that I'm doing is in the opposite direction. So it's
Oh, and when we're going down, it doesn't count because it's orthogonal.
exactly.
Okay.
So here you have E, which is in this direction, but dl is orthogonal.
And the dot product of that is 0.
It's 0, okay. Here's the same. Here we are going, this direction is positive, this direction is negative because the unit vector is opposite, and here you have E, which is radial, and in each point, since I chose this curved surface, this curved, sorry, not surface, line, dl is tangential, which means that in any point will be orthogonal to the electric field. So here the contribution will be 0, and here as well.
0.
Okay. So in all, this is a special shape which is easy to see. Not an easy line, an easy line.
Yes.
But this applies to any sort of line. So even if you have another line which is slightly different,
Squiggly line, yeah.
it's still the same, as long as you go back to the origin, to the starting point. Okay.
Okay.
Again, this applies now because you have this shape of the electric field. Let's leave this.
It doesn't look like it's picking it up.
Okay.
Wow. I'm not. Yeah. Whatever.
So you have to watch the electric field how it's shaped. If the shape of the electric field is like this, uniform,
Then it's easy.
then it's conservative.
Oh, yeah, it's conservative.
Yes, it's conservative because you don't lose any energy. It's conserved.
Yes.
So you go start from here, there. As long as you return back to the starting point, you don't lose any energy. Somewhere the energy goes in, somewhere goes out, but
It's conserved.
it's conserved.
Yes.
It applies here, where you have this field
A
created.
uniform field, yeah.
Or it applies even here, where you have
Radiating field.
a radiating field. There is one particular shape of electric field where this doesn't apply anymore.